Okay, everybody, let's break down that last experiment, but theoretically, not actually with cards. And when you get done, you'll begin to understand how card counting works, which is actually pretty cool. So the experiment started with a shuffled deck of 52 poker cards. Pretty straightforward. So we started over here, and then we pulled the first card. Now, there's lots of things we could have measured in that experiment. We could have measured, like I said, the rank, the color of the card, whatever. But I chose to focus on the suit just because we focused on that before. So in particular, I was focused on the suit of hearts. So really, we can make this a two-outcome experiment by saying either we get hearts or we don't. We can make it simple. Either we get hearts or we don't. And I bet y'all figured out the probabilities of those things. For example, if you break down a deck of cards, I think we talked about this a couple days ago, there are 4 suits, and there's an equal number of each of those suits in the deck. So a deck of 52 cards, there are 13 of each of the suit, ace through king, of each of hearts, diamonds, clubs, and spades. Okay? So the chance of getting hearts is 1 in 4, or 25%, however you decide to look at it, 1 in 4, 25%, because it's 13 out of 52, okay? The chance of not getting hearts has to be everything else, so it's either 39 out of 52, or probably easier to say 3/4, or 75%, depending on how you want to express that. Now here's where it gets interesting, in my humble opinion. After that first card, if you leave the card out and then grab a second card, this, I think, is where it gets interesting. This is where it gets interesting. Now, we did have this happen. So I'm not going to focus on this one. We saw a heart come out. My next question is, assuming you saw a heart here, what's going to happen on the second card? Well, there's still 51 cards left in the deck. You pulled the one out, it's hearts, it's out. But there's still 51 cards left in the deck. So that means there's still potentially hearts that you could get. Or there's still potentially not hearts that you could get. And I think that at this point I asked, is the chance of getting hearts greater than, less than, or the same as it was back then? And you scratch down your answer, of course. And this is where it gets fun. It's not the same, because you took a heart out. That means you no longer have 52 cards in the deck. You now only have 51 cards in the deck. And of the 51, there are only 12 hearts left. The probability of getting hearts just went down a little bit. And the probability of not getting hearts just went up a little bit. Check this out. Okay? 39 out of 51 has to be bigger than 39 out of 52. The denominator is smaller and the numerator is the same. That means this probability has to be bigger than 75%, thus necessitating that probability to be less than 25%. They have to add up to 100%. Once you pull a heart, 100% of the time you're either going to get a heart next or you're not going to get a heart. These two, you can actually see 12 plus 39 is 51. These add up to 100%. Since this one is greater than 75%, this one has to be less than 25%. Pretty cool. And then we did one more. Third card. Third card. We did one more piece of this experiment. And we got a heart a second time. We were also here again. So this is our experiment. So, once again, there's still a bunch of cards left in the deck. There's still a bunch of cards left in the deck, and some are hearts. And my hearts are getting worse as I go left to right. I apologize. And some are not. But now you've removed 2 cards from the deck. 2 cards. And there's only 50 left. And of those 50, 39 are still not hearts. You pulled 2 hearts out. That means all the cards left in the deck are still not hearts. 39 out of 50 is 78%. that means you only have an 11 out of 50 shot, or 22% chance of getting a heart next. See how it went down from 25% down to 22%? And the chance of not getting a heart is going up from 75% to 78%. That is an interesting application of probability. With a die or with a coin, it didn't matter what one flip was or what one roll was. The next flip, the next roll had the exact same probability. This is the reason why you don't count roulette wheels, nor count craps, nor count one-arm bandits. All these games in Vegas, from trial to trial, the outcomes are independent of what happened before. They have no bearing. What happened before has no bearing on what's about to happen. But cards, you've heard of counting cards. Everybody's heard of counting cards. It's a great way to make money over the long run in Vegas if they don't catch on that you're doing it. Counting cards relies on this fact right here, that when you see a card that is then left out of the deck, downstream, it changes the probabilities of what happens. That's why you can count cards. If you can keep track of what's going on in your mind, you can actually establish these chances as you go. So that's the difference between what are called independent events and dependent events. Rolling a die, flipping a coin, those are called independent events. Because you flip a coin, that coin has no care in the world what happened in all the flips that happened before. It's going to be 50-50 the next time. Even odds for heads or tails. Same with a die. You throw a die, whatever you get, there's a 1 in 6 chance of that number happening. It doesn't matter. It doesn't matter if you saw 16 sixes come down the pike. The next roll, the chance of a 6 is still about 17%. Still about 17%. This is a little bit mind-bendy. It goes against human nature, because humans want, if you see a die rolling a bunch of a certain number, you want it to correct. You want that definition of probability to kick in right then. The idea of 17% over the long run. But you gotta remember, those little tiny blurps that we see are very, very short runs in the grand scheme of probability. So those independent events, the previous events have no bearing on what's coming later. But with cards and eggs, we'll go there next. But with cards, you can keep track and you can count and you can refine the probabilities as the cards come out. And that's what makes cards and dice. I love the fact that both are in casinos and both have their own place in casinos. Probabilistically, they're very different. Let's look back at Russian egg roulette.